Hello and welcome to this AM Aerospace session at the AM Industry Summit. My name is Israr Kabir with ASME's Industry Events. During the session, please use the chat box to enter questions and interact with the other audience members. We will answer as many questions as possible at the end of the session. Please join me in welcoming our speaker, Dr. Eduardo Barocchio, Assistant Director of Additive Manufacturing at Purdue University. He will discuss design of large-scale 3D printed composite compression molding tools. While attaining his PhD, Dr. Barocchio and his colleagues developed the Composite Additive Manufacturing Research Instrument, also known as CAMRI, and its physics-based simulation workflow for extrusion-based additive manufacturing processes. Dr. Barocchio, the session is yours. Please take it away.
Thank you so much for the introduction. So today we'll be talking about the application of large-scale 3D printing composites for compression molding tools. So once again, my name is Eduardo Barocchio. I'm Assistant Director of Additive Manufacturing at the Composites Manufacturing and Simulation Center at Purdue University. And I'm really happy to share the outcome of this project with everybody today. So just a brief introduction of who we are at the Composite Manufacturing and Simulation Center. So we are the design, modeling, and simulation technology area for IACME, the composites industry. So we have capabilities for both experimental characterization as well as lab scale manufacturing processes for different composite manufacturing techniques. And we have project partners all across the automotive and aerospace industry. So today, we're going to be looking at this case study of a compression molded blocker door. So for some of you who don't know what a blocker door is, that's basically part of the thrust reversing system in a jet engine, so that helps redirect the flow to slow down the plane. So we can see here the metal, a legacy metal design. This basically component is hinged on one side and then it's actuated at the middle to basically redirect the flow. So basically, the component is subjected to wind loads, and that makes it this type of application made it suitable for compression molding or a drop-in composite made by compression molding of PPMC or pre-preg platelet molding compounds. So in order to produce this part of composite, we need a double-sided tool. So in this case, we see the negative side of a additively manufactured tool. So this tool was produced in the LSEM system by Thermwood. So we can see on the right-hand side, the negative tool, and on the upper right-hand side, the positive tool. So we can see also some indexing rods used for the alignment of both tools. And throughout this presentation, I'm going to walk you through the process that we follow to design not only the molding tool, but also the molding process, and driven by digital twins. So as part of our work at CMSC, we have developed digital twins to support the design process and integrate those to drive the design process for composites materials, in which, it starts with the material properties, comprises the tool geometry, the processing condition. Then we can evaluate the performance of the manufactured part, considering the effects of manufacturing, and then study or analyze how the part will perform in the intended assembly. So as part of that strategy, we have developed what is the Composite Virtual Factory, in which we integrate different commercial codes as well as emerging codes and custom developed codes to integrate those into process-specific applications that allow us to simulate the process, the manufacturing process for example, additive manufacturing, injection over molding, high-pressure RTM, or compression molding. So these are some examples of those integrated workflow applications. So we'll be looking primarily today at the additive manufacturing workflow that incorporates a geometry piece of software, which is in this case CATIA, then the slicer simplified here, that is Simplified 3D, then the Extreme or Digimat that provides some of the input materials properties, and then Simulia, which is the primary tool, the Abaqus by Simulia, which is the primary tool used in our process simulation. So also having this digital thread of the manufacturing process allow us to have a continuity across the different geometries. So for example, the different geometries we'll have in this example includes the geometry, the nominal geometry of the part that we need to produce, but we also have changes in shape when the part is subjected to the wind loads or is under operation. We also have a different shape when the part is manufactured and is still the processing temperature inside the mold. And on the other side, for the mold, we also have a different mold shape. So one, for example, is here when the mold is at the processing temperature of the thermoset system used for making the part. We also have a nominal, the mold shape with a nominal dimension and the geometry that we use for printing. So in this case, all this geometry continuity is satisfied through CBF Hub and basically different simulation workflows that we have developed. So for this particular example, we use PPMC 3D, which is for the molding piece of the problem, and we also use Additive 3D for driving the design of the printed tool. So our focus will be primarily on Additive 3D. So going a little bit under the hood of what is in Additive 3D. So basically, there are two key components to start with. One is the AM system card that contains all the characteristics of the printer, such as boundary conditions, how the deposition strategy affects the orientation of the fibers within the printed bead, etc. And that fits the material card. So the material card provides all the material properties that are required for performing not only the simulation of the printing process, but also to analyze the performance of the printed part. So as part of the process simulation, basically it's a physics-based process simulation. We start with the geometry, then that is transferred into the slicer where we discretize that geometry into a set of layers and individual beads. Then as an outcome of the slicing, we got the machine code that is used for driving the system. In our case, the same G code is going to use for driving a sequentially coupled thermomechanical analysis. So we first solve a heat transfer analysis to solve for the temperature, for the bonding between layers, for crystallinity in the case of printing with a semi-crystalline polymer, etc. And then we pass that into a stress and deformation analysis. So we can then go through this loop to basically come up with either a geometry or a slicing strategy that will mitigate large deformations or excessive stresses that can lead to the lamination or to failure of the printed part. Then we can move to the next step and do a performance simulation. We can take the effects of manufacturing to inform a performance analysis. In the case of the compression molding tool, we are interested on the shape change. So we can, for example, iterate with the shape so that we can develop the geometry or create the geometry that when it's using the service conditions or temperature conditions will provide the right shape. Or we can also basically use carry out a performance analysis to see analyze the heating and cooling of the compression molding tool. And we will talk a little bit more about that. So we have done efforts to basically simplify this simulation workflow. So to the extent that you can only basically focus on selecting the machine, select the material, select the geometry, pick your slicing options or slicing flavors, then run the analysis, and then just focus on reviewing the results without going into all the details of what's under the hood of the simulation workflow. So in terms of the technology that is behind the simulation workflow, so our primary tooling using here is Abaqus from the Simulia brand, from the Sol system. So we basically use the machine code output by the slicer, transform into what we call an event series to activate elements into a finite element mesh. And we capture multiple phenomena that develop simultaneously during the printing process, including autotropic heat transfer, polymer crystallization and melting in the case of semi-crystalline polymers, interlayer bonding. We even capture local convection coefficients or conditions that develop inside the different printers. The heat losses removed by a compactor in case of using a material, either a roller or a tamper for consolidating the printing material. there is heat removed by the action of the compaction mechanism, so we can account for that. But at the same time, we also capture the anisotropy in the shrinkage, in the viscoelastic behavior of a printed material. So this is important in order to capture the physics that underlie this manufacturing process. So going a little bit in details of the material inputs that we need to create the digital material card. So we combine both experimental characterization with virtual characterization to generate the inputs for different material models that we use in our simulation, our physics-based simulation workflow. And in terms of the system card, so we also need to consider the different conditions developed inside the printers. For example, how is the part attached to the substrate, the heat losses developed inside, how is the bit deposition strategy performed, and how that affects the fiber orientation distribution within the bit. So that fits into the system cards, which we have developed for Cambry, which is our system that we develop at Purdue, as well as commercial large-scale systems like the LSAM and the BAM from Cincinnati. So this basically provides some of the inputs that we need for the simulation that are concerned with that are specific to each machine. So now looking at the workflow for designing this tool with Additive 3D. So we will be looking here on the right only at the negative side of the tool. So this is the geometry of the nominal shape. So this is basically a simplified geometry which was 3D printed, and then we perform the 3D printing simulation. And then after simulation, in this case, simulation of the printing process, we basically then simulate the process of removing material due to the machining, and then we look at the performance. In this case, we are concerned about ejecting the part from the mold as well as the heat transfer characteristics. And we can see, just to kind of give a brief overview of how the process performed. So we have the negative and positive tool. We have a molding charge drop inside the tool. Then the system is heated, compression molded. Then we release the positive tool. And then the part is ejected. And we have the blockador geometry. So now looking first into the process simulations. So as inputs, we need the machine code that was output by the slicing. We just select our system card, the material card, and basically we can perform the 3D printing simulation. So we can see an example of the simulation results in here. So on the left-hand side, we can see the temperature. On the right-hand side, we can see the stresses. In this case, the stresses are in the stacking direction. So we are concerned about the stresses that might develop during the printing process and cause the part to cause lamination or failure of the part during the printing process. So we can see here in temperature, the process is highly non-isothermal. So the bottom is cooler than the top, and the material cools down as it is deposited layer by layer. So those temperature gradients lead to stresses, residual stresses, as well as the anisotropy of the printed material. So we can see some stresses developing at the bottom. Then once the part is released from the build plate, some stresses also develop. And then upon cooling to room temperature, different stresses state develop. But mostly it's under compressive stresses, which is not really critical for this application. So we will not focus on okay, what is the effect of the different printing configurations. So we can certainly print this part horizontally in a horizontal configuration or in a vertical configuration. But since the direction that we use for printing the part affects how is the material oriented and what are the properties of the printed material and the performance of the printed geometry, we want to ensure that in the loading conditions that we have, both in molding as well as once we eject the part, we don't compromise the integrity of the tool. So here, basically, following the printing process, we perform a stress analysis, considering these two cases of print configuration. So on the upper side, with the tool printed vertically, we can see basically that during the ejection process, we don't get significant stresses that can cause lamination. However, if we do the other printing configuration, we can have some stresses localized in this transition that can lead to the lamination. So therefore, this was the choice for the print configuration. Now, the next challenge we have is to heat up the tool to the processing temperature of the material system that we want to compression mold. So in this case, even though we have a 25% carbon fiber reinforced polymer, the thermal conductivity is still relatively low since it's governed by the polymer, and therefore it's not as straightforward to reach these processing temperatures as in traditional tools. So in this case, the material system is PSU, reinforced with 25% by weight of carbon fiber, and it has a T sub G of around 212 Celsius. The material we use for the compression molding is provided by Dow and is Bora Fuse. It's a carbon fiber PPMC, and is processed at 150 Celsius or 300 Fahrenheit. And the molding conditions we need to produce this part is 10 megapascals at the same processing temperature. So it's around 1500 PSI. So this is a fast cure system. It only takes around 5 minutes to cure a part. So just basically subjecting the part to, and this is one of the analysis we perform to inform the manufacturing process. So if we heat up the tool, only relying on conduction from the platen and natural convection, as you can see, we can barely reach 72 Celsius at the top and 65 Celsius at the top of the negative tool, which we need to think a little bit out of the box to see how we can reach the processing temperature in here. So we evaluate different options. Another option was using or enclosing the hot press and basically introduce forced convection conditions in the inside. So by doing so, we can, as you can clearly see here, we can reach higher temperatures as the processing temperature. And now a third consideration with it was inserting cartridge heaters with controlled temperature at each of those cartridge heaters. So with this approach, which was the one was finally implemented by Thermwood, we were able to reach processing temperatures that are closer to our target processing temperature of 150 Celsius. So that was the chosen solution, was using the heat from the platens in the hot press plus the cartridge heating. So we can see here on the right, the tool mounted on the hot press. In the middle, we can see the tool being closed inside the hot press, and a thermal camera that we use for monitoring the temperature at the upper and lower sides of the tool. And then here, the molding charge being ready to be dropped in the mold. So prior to dropping the molding charge, we record the temperature at the top and bottom. You can see we're very close to the processing temperature, which is in fairly good agreement with what we predicted with our performance analysis. And we were able to successfully mold a blockade door geometry with this PPNC material. So, and after the molding process, the tool remained intact and just with minor signs of wear. So overall, the mold cavity was filled completely. There are some areas that are resin rich, but this was kind of the first trial we did, and these are resin rich areas are, can be overcome by improving the processing conditions. But overall, the molding process was successful. And finally, as conclusion, so we demonstrated the applicability of this 3D printed composite tooling for rapid prototyping of compression molding tools, and use simulation for guiding the design for 3D printing, so that we were able to demonstrate the compression molding tool used by produced by 3D printing to produce this blockade door geometry. And finally, I would like to acknowledge my colleagues at Purdue who were involved in this project, as well as our industry partners, Thermwood, for providing the printing of the part, Thermwood for providing the material for printing the tool, and Dow for providing the material, and Dassault System for the support with all the simulation tools. And with this, I will be happy to take questions that you might have.
Thank you, Dr. Verrocchio, for this very insightful presentation on the composite design. What are some of the next steps in your research? Do you have sort of advanced steps plan to actually implement this into just some sort of commercial solutions?
So we are currently extending the simulation workflow, Additive 3D, to capture not only different printing systems, because there are variations from printer to printer, even though you can use the same material, and variations that result from flow conditions that develop in the nozzle as the material slick down, or even in terms of for example, the substrate that is used for holding the part. Some printers use, for example, a sheet of plastic. Some other printers use a adhesive, and those have consequences, on the deformation that can develop in the printed part. So we are basically working on extending our simulation capabilities to basically capture those different specifics of the different commercial printers, and also on characterizing different material systems, so that we can offer basically different solutions in terms of material capabilities. And as I mentioned briefly, we are also working on making the simulation workflow user-friendly, more user-friendly, so that basically anyone can set up an analysis and just focus on selecting a printer, selecting a material, and be able to run a simulation. The other part that we're also working heavily is on more validation. So it's important that we do more experimental validation to build more confidence on our simulation tools, and also improve on the different models that we might need to capture a greater level of detail.
Got it. And earlier in your presentation, you had shown that you did some work with digital twins. So is some of this data analysis and capture that's going back, is that sort of going back and helping you to shape those digital twin models as well?
So yeah, basically, as I guess we use I would use interchangeably that word between digital twin and simulation workflow. Basically, the simulation workflow is a digital twin of the manufacturing process, and allow us to track all the effects of manufacturing into the performance analysis, for example, or consider those effects into the performance analysis. And there's a big piece of material characterization that goes into that, and the idea is basically to connect all those dots. Right now we have well connected basically all the way from the simulation, all the pieces of the simulation. We are basically also working more to create a stronger connection between the material and material characterization and simulation. And specifically what I mean by that is, let's say, so that we don't, at this, I guess, what we're working on is to basically reduce the amount of experimental characterization we need to do to simulate the printing process with a given material in different systems. So to date, if you want to simulate the printing process in different AM systems, there is an extensive amount of characterization that has to be done. So we are basically working now on creating that piece of the digital twin that allow us to predict material behavior, predict properties for different printers.
Got it. Okay, thank you. So with that, we'll take some audience questions.